So I will continue from the previous video. So like this is kind of like a part 2 of the previous video. Yeah, like now we can actually jump off to what's really happening in the transporting material during pump. So we can see what's actually theoretical background and so on. The challenge arises in the transportation of the specified concrete mix due to the presence of large aggregate particles and variations in the water to cement ratio. So achieving high viscosity in fresh concrete is crucial for retaining shape during printing, 3D printing, requiring relatively elevated or high pumping pressures, ranging from 1 to 4 megapascals, which means like 10 or to 40 bars. The high pumping pressure may lead concrete material to have a segregation, which is not desirable property at all. To avoid segregation, adjustment of the appropriate adjustment in the concrete mix are necessary under these high pressures to form the thin smearing layer for good pumpability. Basically, the balancing the feeder system, nozzle, and the material properties is important for optimal printing, potentially necessitating adjustment in pumping speed based on the size and the shape of the printed object. Within the pipe or hose, the concrete material exhibits laminar flow behavior. However, estimating pump pressure for laminar flow of a beam fluid through a pipe can result in an overestimation of the flow rate by several folds, with studies revealing potential discrepancies of up to 5 folds. This overestimation is a result of the development of a lubricating layer on the pipeline walls due to the shear-induced particle migration, sometimes called the SIPM. The shear-induced particle migration refers to the migration of particles within the suspension when subjected to non-uniform shear forces on the shear plane, causing particles to move perpendicular to the shear plane. This phenomenon impacts particle concentration and size profiles, leading to radial viscosity variation in the flowing suspension. In concrete containing aggregates, large particles tend to migrate toward to the center, while smaller particles concentrate towards the wall due to their varying responses to flow conditions. The lubricating layer or smearing layer, or very actually the smooth thin layer, forms a thin film near solid surfaces in flowing suspensions, acting as a lubricant that reduces friction between the suspension and the pipeline walls. The lubricating layer's yield stress and plastic viscosities are typically about 1/5 and 1/15, respectively, compared to the bulk materials. The shear stress, shear rates, and velocity profiles of the concrete during pumping can be seen here. Concrete's shear stress and shear rate profiles during pumping illustrate the zero shear rate at the pump central axis and maximal values at the wall. When shear stresses at the radial positions exceeds the concrete bulk yield stresses, the shearing of the bulk materials that started to happen. Based on concrete properties and pumping conditions, concrete can flow in either slip flow mode, very thin slip layer with an unsheared plug, or slip plus shear flow mode, slip combined with partial shear of the bulk material and the plug. So the researcher like Kaplan developed an analytical model to predict concrete pumping pressure in slip and slip plus shear flow mode using rheological parameters and pipeline geometries. In continuous extrusion with stiff materials, yield stress and plastic yield the viscosity typically ranges in the few hundred Pascal and few Pascal second respectively. I can also give you the desirable rheological requirement or the variables for better pumpability. So the ideal rheological characteristic needed for pumping often are in competition with those favorable in respect of the material's behavior post-deposition, which is a shape retention or extrudability or buildability. Generally, printable concrete needs a robust static high yield stress to counteract gravitational and other forces upon deposition like dynamic and some other forces. However, the effects of high structural buildup and thixotropic rates in 3D printable concrete are not really actually favorable for the 3D the pumpability. And also, they are not the pumping behavior with the interaction with them not yet thoroughly investigated. Researchers like D. Shooter and Face highlighted the challenges, stating that short interruption during pumping lead to major difficulties in resuming pumping operations due to the sometimes tremendous effect of internal structure buildup. For instance, the large-scale pumping trials revealed a 50% increase in pressure loss after a mere 20-minute delay for a mixture with a structural buildup rate affix of 0.3 pascals per second. Basically, every second it builds up with a 0.3 pascal in their yield stress. Despite elevating pumping pressures to 35,000 kilopascals, resuming operations after the delay proves unfeasible. Basically, it won't be pumpable at all. Consequently, pumping high yield stress concrete or chemically accelerated concrete might not be optimal for large-scale extrusion-based additive manufacturing. So there's an alternative approach which involves transporting low viscosity, low yield stress concretes over long distances and activating them at the printhead just before deposition. This method relies on inline or second stage mixing station techniques to ensure accurate dosing and uniform distribution of the admixtures. Even in scenarios of free flow deposition, it remains essential to guarantee the rheological properties are sufficiently robust to prevent filtration under high pressure or the segregation. Characterizing the pumping relevant rheological properties of concrete and the lubricating layer, as well as predicting pumping pressures, presents significant challenges. The inadequacy of empirical design charts, primarily reliant on slump or spread parameters, has been addressed with the recent advancements in test approaches, various test approaches, and prediction models. However, most of these methods demand precise quantification of the rheological properties of concrete and the lubricating layer, which has been challenging for high yield stress printable concrete. The pumping process can influence the rheology of concrete, such as dispersing cement particles at higher shear rate, activating residual superplacizers, or inducing air through pistons. Nonetheless, prior observations on changes in concrete yield stresses due to pumping are inconclusive yet. Such alteration could significantly impact the extrusion processes, continuity, or the stability of resulting layers, necessitating further research to develop inline rheology monitoring tools that can be integrated, for instance, into the printhead or the end nozzle and effector. I think it's about time to wrap up today's video, or to wrap up the part 1 and part 2 of the pump theory. So as we concluded today's session, we've explored how materials behave in the unique environment of pumping with desirable rheological requirements. In the previous session, we actually looked into the different types of the pumps being used in the 3D concrete printing and how they are working. So we looked into the underlying mechanisms as well. So thank you for your attention up to the stage, and see you in the next video, which will be dealing into the more practical side in 3D concrete printing related to the pumps. So yeah, bye for now.